Before we move into linear regression, we're going to review linear functions a little bit. So a survey undertaken in a school asked how many hours per week a student spends on social media as X and sleeping as Y. It was found that there's a linear correlation between the two variables, and the equation of the regression line is Y equals 50 minus 2X. State the value of the gradient. In the US, we use the word slope. Slope and gradient are synonymous. And the Y-intercept of the regression line, and interpret both of those meanings in context. So go ahead and pause the video and try that. So for the first part, gradient, remember gradient for a linear equation, this is in slope-intercept form here. So our -2 right here is our gradient or our slope. So our gradient is -2. Gradient or slope is your change in y over change in x. This little triangle here, delta, means change. So that in this case, our y was our sleeping hours and our x was our social media hours. So it's the change in sleeping hours over the change in social media hours. So for this to be equal to -2, what that means is for every hour of increase in social media use, so every time social media use goes up by 1, the hours of sleep is going to decrease by 2. So for every 1 hour of increase in social media use, the number of hours of sleep decreases by 2. For your y-intercept, again, this is slope-intercept form, it's just written backwards. So our y-intercept is 50, which means when x is 0, y is 50. So that's saying that if someone was on social media for 0 hours, they would sleep for 50 hours. Obviously, in context in this case, this does not make sense. You can't sleep 50 hours in one day. So it doesn't matter if you use 0 hours of social media, that wouldn't be possible. So lesson 6.2, we're going to be talking about the line of best fit or regression lines. I would pause the video and write down these vocab words. So the first one, line of best fit, that's a line that can be drawn on a scatter diagram that shows the trend followed by the data points, and we can use it to make predictions about data that we don't have. Residuals is the difference between your y value and the predicted y value. This error is how you find the best line of fit if you're doing it by hand. By hand, the way you would calculate your line of best fit is y minus, remember this bar notation means the mean of the mean of the y coordinate. So mean of the y coordinate is equal to your slope, which is s sub xy, which is the covariance of x and y, divided by s sub x, which is your standard deviation of x squared, times x minus the mean x coordinate. This is if you're doing it by hand. In this class, you'll always be using a graphing calculator unless you're using it on your internal assessment. But this is how you would calculate your line of best fit by hand. To draw a line of best fit by eye, for example, if you're trying to graph it, you would find the mean point. So you'd find the x bar, y bar, so mean of the x's, mean of the y's. You'd plot that, and then you draw your line through the mean point, balancing the number of points that are above the line and below the line. So this first example gives us test results in math and biology for 8 students, where math results are X and biology results are Y. So first we're going to do parts A through C. Find the mean of the math scores, find the mean of the biology scores, and then I want you to draw a scatter diagram or a scatter plot and plot the mean point that you found in parts A and B. So go ahead and pause the video and try that. So if you use a calculator, you find that x bar, or the mean of all the math scores, is 32.75, and if you use your graphing calculator or do it by hand, you find the y bar, or the mean of the biology results, is 25.375. And this is the scatter diagram. So again, I labeled and scaled my x-axis, math scores, labeled and scaled my bio scores, and then I plotted in red. These are all the data points, and then in blue, that's the x bar, y bar. So this is our mean point. So then if you haven't already done so, we want to draw by eye a line of best fit. So again, we go through the mean and you try and get as many points above the line as below the line. So go ahead and pause the video and do that. So here's my line of best fit. It goes through the mean point here, and then there's a few points here that are below the line, and there's a few points that are above the line. It's not going to be necessarily perfect. Obviously, use a straight edge. And sometimes we'll be talking about finding an additional point, like a y-intercept, and that will help you draw your line. So then the last part is using our graph here to help us predict a result of a biology score, given that we know somebody has a math score. So we can see that there's a pretty strong positive correlation between the biology and the math scores. So we can do this similar to what we did on the cumulative frequency graphs, where if we know we want our x-coordinate to be 40, we can follow our graph up and figure out what our biology score would be. So go ahead and pause the video and use your line of best fit to estimate or predict what a biology result would be for someone who got a 40 on their math test. So again, I did this the same way we did our cumulative frequency graphs. We knew our x-coordinate we want to be 40, so I followed the graph up until I hit my curve, and then I went across here and got 31. If your line of best fit is not exactly the same as mine, you may have ended up with a slightly different prediction. It should still be close, but again, it's follow through, so as long as it follows through from your graph and you show your drawing on here, you'll still get credit for that. So the next example, at a coach, which is a bus station, the maximum temperature in degrees Celsius is X and the number of water bottles sold is Y, were recorded over 10 consecutive days, and there's the data. So go ahead and pause the video and do parts A through C. So plot the data points on a scatter diagram just on your graphing calculator. Comment on the correlation, so qualitatively, and then also find the quantitative Pearson's product moment correlation. And then while you're doing that, write down your regression of y on x from your graphing calculator. So I use Desmos to do my scatter diagram. So here's our scatter plot. X is temperature, y is water bottles. And it has a pretty strong positive correlation. So I would say for part B, I would say strong positive correlation qualitatively. Quantitatively, if you actually calculate the R value is 0.931. So definitely a very strong positive correlation. And then using your graphing calculator to find the line of regression, I found that A was 8.04554 and B is negative 24.746. So three significant figures. You get y equals 8.05x minus 24.7. So then part C wants us to interpret the meaning of the slope and the y-intercept in context, and do they make sense? So go ahead and pause the video and do that. Okay, so for the gradient, you have 8.05. Remember, slope and gradient are synonymous. Change in y over change in x is change in water bottles sold divided by change in temperature. So that means that for every 1 degree Celsius increase in temperature, the number of water bottles sold increases by about 8. Yeah, that makes sense. If it gets warmer, you're going to probably sell more water bottles. For the y-intercept is negative 24.7, which means you have the coordinate point 0, comma, negative 24.7. So if it's 0 degrees Celsius, which is freezing, that's our 32 degree Fahrenheit, negative 24.7 water bottles would be sold. No, this doesn't make sense. You can't sell negative water bottles. They're not going to be buying back water bottles because it's freezing. Part E, so the temperature is predicted to be 19.5 degrees Celsius. Use your line of regression, your equation that we found in part C, to predict how many water bottles should be stocked. So they're giving us our x-coordinate, temperature is our x-coordinate, and we want to figure out our number of water bottles sold, which is our y-coordinate. So go ahead and pause the video and try that. So we know our x-coordinate is 19.5, so we just plug that in for x in our line of regression here. So you have y is equal to 8.05 times 19.5 minus 24.7. You could also use the completely unrounded version as well, which means your numbers would be slightly different than mine. Plug that in, you get 132.275 water bottles. You can't have, a quarter of a water bottle, so in order to achieve this, they need to make sure they have at least 133 water bottles. So in this example, we have 12 students to see if there's a linear correlation between height in centimeters x and shoe size in y. So they give us our data here, and I want you to go ahead and pause the video and do parts A through E. Plot on a scatter diagram, comment and find the correlation coefficient, find your regression equation, interpret the slope, and also estimate the shoe size of somebody who is 163 centimeters tall. Go ahead and pause the video and do parts A through E. So here's my scatter diagram. Again, label your axes, height in centimeters, and shoe size. And it's a pretty strong positive correlation. So part A, strong positive correlation. Part B, the reason that it is valid to use a linear regression is because if I look at this, I can see there's a pretty strong linear positive correlation. So then using my graphing calculator to find the regression equation and the Pearson's product moment correlation coefficient, I found that the regression equation was y equals 0.154x plus 12.0 rounded to 3 significant figures, and the correlation coefficient was r equals 0.854. So then interpret the meaning of the slope and the y-intercept, and does it make sense in context? So the slope or the gradient was 0.154, which is the change in y over change in x, change in shoe size over change in height. So every 1 centimeter height increase, shoe size also increases by 0.154. Yes, it makes sense in context, except for the shoe size doesn't increase that way, but it's a good model. And then y-intercept, 12.0, so that means you have the coordinate 0, comma 12.0. So if someone is 0 centimeters tall, their shoe size would be 12.0. That doesn't make sense. You cannot be 0 centimeters tall, and if you are 0 centimeters tall, you're not going to have feet to therefore have a shoe size. Part E, estimate the shoe size of a student who's 163 centimeters tall, so shoe size is y, height is x, so I plugged in x to be 163 and found 37.102. You can't have a decimal shoe size, so a size 37. It is reliable because 163 centimeters is an x value that's within the range of data collected. So this is an important thing when you're doing what we call interpolation. Your data, what you're trying to interpolate, what you're trying to predict, it has to be within the range of data that you've already collected. Okay, so for example, I can't use this to estimate the height of somebody who's 200 centimeters tall because that's outside of our data range. Okay, and we also only predict when we're given an x coordinate because that's the independent variable. So using that information, answer questions F and G. Why is it not reliable to use the regression equation to estimate the shoe size of someone who's 150 centimeters tall? And why is it not reliable to estimate the height of somebody who has a shoe size of 38? So for part F, it's exactly what we just said. 150 centimeters is outside of our range of data that we collected, so it's unreliable. Our predictions are only reliable within the range of data that we collected. And then part G, we only predict dependent variables given independent variables, not the other way around. So you can never predict an x coordinate with a given y coordinate, only the other direction. The last part of this section is piecewise functions. So sometimes one linear function is not enough to represent the entire situation. So we can use piecewise functions, which means parts of the function are created using different line segments. So for example, if you have someone who's walking at a constant speed and then they stop at a coffee shop to drink, with y being their distance traveled versus x being time, this is what their function would look like. So you can see between 0 and 20 minutes, they have this constant increase in distance, which they're defining to be f of x equals x plus 10. And then at 20 minutes, you can see they stop and they're sitting and drinking coffee because their distance is no longer increasing. So now we just have f of x is equal to 30. So then the function for this, we define it with the different pieces of the function, and then we define it with x intervals. So f of x is equal to x plus 10, where x is between 0 and 20, and then 30 when x is greater than 20. So now different things are happening at different times, and we can represent that as a function. So here we're given a piecewise function f of x is equal to 4 when x is between negative 2 and 3, and f of x is equal to negative x plus 7 when x is between 3 and 7. So first thing we want to do is find f of 0 and f of 6. So remember, this is function notation, which means basically this is asking what is your y coordinate when x is that value. So go ahead and pause the video and find f of 0 and f of 6. So for the first one, they want us when x is 0, what is y? So I go to the intervals here and I find where x equals 0, what section of the function that occurs, and that occurs between negative 2 and 3. So I want to look at this part of the function to answer the question. So when x is equal to 0, y is equal to 4. And then for the next part, f of 6, what is y? So again, I go into the piecewise function, I find where x equals 6, which interval, which is between 3 and 7. And I want to use this part of the function to find my y coordinate. So I'm going to plug in 6 for x. I get negative 6 plus 7, which is equal to 1. So go ahead and pause the video and try parts B and C if you haven't already done so. State the domain of this function, and then graph it. So for the domain, when you're doing a domain of a piecewise function, just look at the intervals here. What's the smallest x that they show us? The smallest x is negative 2 included. And then we go all the way up to 3, we include 3, and then everything bigger than 3 up to 7 included. So our total domain for our function is negative 2 is less than or equal to x, which is less than or equal to 7. Or if you write it in interval notation, negative 2 to 7 with brackets for included. And then our graph, so again, scaling the axes here, they didn't give us any context, so I didn't label. And then between negative 2 and positive 3 in the x's, our y-coordinate is always 4, so you have a horizontal line here. And then between 3 and 7, it's the line negative x plus 7, so so it has a slope of negative 1, so it looks like this. So this has been linear regressions and interpreting linear regressions and piecewise functions.